In recent years, there's been an explosion of interest and excitement and scientific research into exoplanets, planets that orbit other stars. And going along with that is an increasing recognition that the knowledge we've learned from the planets in our own solar system are very, very important to understanding and inferring the properties of planets around other stars. One of the most important properties of planets is their composition, which tells us how they formed and what their structures are. And all of this is important if we're interested, for example, in finding another Earth. We would like to know, if we find a planet around another star, if it's Earth-like, if it has an Earth-like composition, an Earth-like structure with an iron core and a silicate mantle and maybe an atmosphere. And there's a great deal of research into this in the exoplanet community, trying to improve our understanding of how we can determine these properties of planets around other stars. In our own solar system, we've visited many planets with spacecraft and can measure the compositions by telescope methods and spacecraft methods. And as a member of the science team for NASA's Messenger mission, which orbited the planet Mercury for 4 years from 2011 to 2014, I did just this for Mercury. I helped measure its composition and determine what it's made out of in comparison to the other planets in the inner solar system. Some of the most exciting discoveries we made with the Messenger mission to Mercury was that Mercury is, in many respects, quite unusual in terms of its composition compared to the other planets. It had already been known that it had a higher density than the other planets and thus has a larger iron core. But what Messenger showed us is that Mercury also differed in its overall chemistry in what we call its oxidation state. What Mercury tells us is that in one solar system, our solar system, the protoplanetary disk that made the planets, there were processes going on that led to this diversity in oxidation state and in the amount of iron relative to silicate that led to a really large diversity just within a single solar system. And I'm going to be discussing the implications of this for understanding the data from planets around other stars. At AGU, I will be presenting a talk in a special session aimed at linking what we know from solar system science to exoplanet science. And in particular, I want to draw lessons learned from Mercury's composition in comparison to the other planets in the inner solar system to what can be inferred from the existing data for planets around other stars. My name is Larry Nittler. I'm a staff scientist at the Carnegie Institution of Washington's Department of Terrestrial Magnetism. I am a cosmochemist and planetary scientist. I study meteorites and asteroids and planets using both laboratory instrumentation and spacecraft to unravel the mysteries of the origin of our solar system.